polynomial in factored form. Now, if I multiplied all of this out, it would be totally a pain. But if I multiplied all of this guy out, I would end up with a positive. It looks like x to the fourth for the first term, right? X times x times x times x. And then I would have to do some crazy distributing and multiply the whole thing out. But I don't have to do that to graph it. All I have to do is find the zeros. All I have to do is figure out the x values that make each of these guys 0. And then I can graph it from using the roots there. So what x value makes this 0? Well, of course, that's x equals 0. X plus 3 equals 0. So x, I guess, is going to have to be negative 3. X minus 2 equals 0. So x equals 2. These are all the roots. And x equals 4. Terrific. So I have a root at 0, at negative 3, at 2. How am I doing so far, Stuart? At 4.
Doing great.
Those are all the roots. Terrific. So this thing looks like it has 4 roots. And how do I know whether it goes like up at the end or down at the other end? Well, again, if I multiply it all out, I would have had a positive x to the fourth for my first term. That's a controlling term. This is a positive x to an even power. So I know when x goes to infinity, in other words, I'm putting in positive numbers, I'm going to end up with a positive value for this first controlling term. So I know it's going to have to go up like this. And I can actually just kind of follow it backwards. I cross here, cross there. Having fun, actually. Go up like that. And it must also go up to positive infinity when x goes to negative infinity. And of course, if I put in a negative big number for x, a negative value to the fourth is in fact positive. So y, in fact, must go in the positive direction as x goes to negative infinity as well.
So let's graph another one of these polynomial functions. And as you see, I set up my x, y coordinate plane just by labeling the x's. I'm not even all that concerned about my y scale at all. And if you notice when Mr. Haas sketched his last sketch, he wasn't really worried about how high up to go or how low to go. We're really focusing on the x values. What happens where? Where are the roots? Where does it cross the x-axis, in other words? Where does it turn around? What's the end behavior? So whenever we ask you to do a sketch of these from a graph, we're not really going to be worried at all about your y values. Okay? So let's go ahead and find out where the roots are. Well, how many roots do we have? If I imagine multiplying this together, I would have an x squared times an x squared. So let's see, it's going to be a 5th degree polynomial. So that means it has up to 5 real roots. Let's see where those roots might happen. I'm going to have to erase this. Let's keep in mind that's going to be an x to the 5th. So clearly, a negative 2 is going to give me a 0 there. So negative 2 is one of my roots. If I plug in a 1, that's going to produce a 0. So 1 is another root. If I plug in a 3, that's going to produce 0. So hold on. It looks like I just have 3 roots. Well, let's go ahead and put these down here. I know I'm going to cross at negative 2. I'm going to cross at 1. I'm going to cross at 3. But wait a minute. I have these squares here. If you recall, what happens when you have a squared term? That's right. I know you answered it back there. It's as though you bounce off of the graph. Remember when you have a parabola with just one real root? Boing, it's tangent to the graph. I sometimes call those double roots. And just to remind me, sometimes I identify that double root. This is just my little goofy system. I just circle it to remind me that's a double root. 1, that's a singular. Okay, why 5? That's not supposed to be a 5. That's supposed to be a 3. A double root. Okay? How are we so far? I just corrected that. Should I go back and fix that? Are we all right? Okay, so now again, I have to figure out how to sketch this. That's when the end behavior can help me. I decided before that this is going to be a 5th degree polynomial, a quintic. And I want to look now at my stretching coefficient. That k value is a negative 3. So let's go ahead and think about that as a negative 3x x to the fifth. That's my controlling term. That's going to be the powerful term when I plug in a super, super big X or a super, super small x. So if I plug in 1,000,000, I'm going to end up getting something very, very negative, something very, very small. So my end behavior is going to be coming down here when I'm plugging in 1,000,000. All right? Let's plug in negative 1,000,000. What happens when I plug in negative 1,000,000? Negative 1,000,000 to the fifth. Well, that's an odd exponent. So negative 1,000,000 to the fifth is going to be negative something times another negative. My end behavior is going to be positive. So, boom, there's my end behavior. Now this is the fun part. I agree with Mr. Haas. This is fun. Now I just go bouncing through. Woo! I'm going to bounce off of that because that's a double root. I think the sound effect really helps. And whooshing through that. Woo! Bouncing off. And down I go towards negative infinity. Again, it's kind of a loosey-goosey sketch, but I see my roots. I see where my double roots are. I see my end behavior. That certainly does look like a polynomial of the fifth degree.
What if I have something, a polynomial, that's not in factored form? This one is in standard form right here. Well, it's an x to the fourth, so I know there could be at most 4 roots. It's positive, so actually I could fill in the end behavior right now. I know when x goes to infinity, again, I'm just looking at the controlling term. When x goes to infinity, this controlling term will get infinitely positive because a positive number to the fourth is positive. So I know I'm going to go off in a positive direction like that. If I put in a negative value, when x goes negative to negative infinity, a negative value to the fourth, that's still positive. So it must go positive in this direction as well. When x goes to negative infinity, y goes to positive infinity. In both directions, it goes to positive infinity. So let's see if I can figure out what the roots are. I think I'm going to have to factor out the greatest common factor here. So let's set it to 0 actually. So I can factor out an x squared, and what's left? An x squared from this guy, a 3x from this guy, and a minus 4 from that guy. I think I'm running out of room. So let's see, x squared, and I'm going to have an x. I'm going to run out of room here, but it's okay. I'm going to have an x plus, that looks like 4, and an x minus 1. Does that do it? Let's see. That do it, Ms. Stewart? I think that works for me. 4x, that works. So my zeros are going to be x equals 0, x equals negative 4, x equals 1, 0. I'm going to use Ms. Stewart's trick. That is a double root. It's an x squared. I'll use your little circlet trick. I have negative 4. That's a root. And I have 1. That's a root. I'm going to get rid of some of this stuff. So those are my 3 roots. And let's see, I'm going to back it up a little bit there. And I already decided that I go off to positive infinity. So I must go through that guy. That's a double root. What am I supposed to do, Miss Stewart?
Boing!
Oh, that's right. Bounce off of that guy, sorry. Down there, bounce off of that guy, and then up to infinity. Bounce off of that, up to infinity. So that is the graph of my function.